So up to now, we know how to decode LDPC codes, and we saw that we get actually very good performance. But we also saw that the decoding performance depends on the parameters of the code, like variable node degree, check node degree. And we saw that depending on the channel, different selections may lead to a better or a worse code. And in this chapter, we're going to analyze LDPC codes and take a look at what's going on behind the curtains to see if we can find an easy way of predicting the performance without actually designing a code and running the code, just from the parameters. So that's what we're going to do. And in the first video, we're going to start by analyzing this decoder for the binary erasure channel. So recall, the binary erasure channel is a very simple channel. And in the binary erasure channel, the analysis of LDPC codes is also very, very simple. Historically, this also makes sense because LDPC codes have been used first for the packet erasures, for packet loss channels or packet protection. And the first analysis was actually for the binary erasure channel. And this analysis already gives a very, very good insight to what's going on in these codes, especially if we have channels with very good quality, with high signal-to-noise ratio. Like an AWGN channel with high signal-to-noise ratio can be very well approximated by a binary erasure channel. We start with the binary erasure channel, and then we'll extend the analysis to more general channels like the AWGN. So recall, binary erasure channel looks like this. We transmit zeros and ones, and we have three possible output symbols, 0, question mark, and 1. And with probability epsilon, we receive an erasure, and probability 1 minus epsilon, we receive the correct value. And now we ask ourselves, what is the necessary epsilon such that the message passing decoder, this iterative decoder, is successful? Successful means the error rate quickly drops and goes towards 0. So we have very small residual error probability. We start with the binary erasure channel because the analysis is very simple. Recall that in the decoder, we only pass two types of messages. Either the binary value, 0 or 1, which is correct, because we never make an error in the binary erasure channel, or we have an erasure. So actually, we have two types of messages, either 0 or 1, or an erasure. And that greatly simplifies the analysis. So let's go ahead, let's get started. We start by looking at the variable nodes. So the channel erasure probability is called epsilon. And now in the variable nodes, we have the channel, the variable node is connected to the channel. The message coming from the channel is erased with probability epsilon. And then we have messages coming from the check node. Messages coming from the check node are erased with a certain probability, which we denote by chi. Chi is the probability that an incoming variable node along the edges of the tenor graph is erased. So that is chi. And what we do in the variable node is we take a few incoming messages and we calculate an outgoing message. The outgoing message depends on dv minus 1 incoming messages and the channel message. And we denote the probability that the outgoing message is erased by C. C is the probability outgoing message is erased. So when is a variable node outgoing message erased? Well, it's erased if all incoming messages are erased. If only one incoming message is not erased, then we know the value of the variable node because it's a repetition code. So one value is not erased means we get everything, combine everything we have, and this is the value of all the incoming messages. So if one is not erased, we are done. and the outgoing message is also not erased. So the outgoing message is erased if everything that's coming into the variable node is erased. So it's erased if yi is erased and all the dv-1 incoming messages are erased. So yi is erased with probability epsilon, and the other incoming messages are erased with probability xi. So, So the outgoing message is erased with probability xi, and this is just because we assume that the messages are all independent. All the messages that come in are independent. So this is the usual assumption that we do. The messages, they are all independent. And because of this, the probability that the outgoing message is erased is epsilon times chi to the power dv-1. So 1, 2, 3, that would be chi to the power 3. The messages are independent, so we can just multiply the probabilities. That's what we do in the variable. Let's move to the check node. So now we denote C as the probability that an incoming message to the check node is erased. Because it's coming from the variable node, we have just calculated C. It's coming from the variable node to the check node, we call it xi. And similarly, chi is the probability that the outgoing message from the check node is erased. So now this is the situation again. We have dc-1 incoming messages are erased with probability xi, and one outgoing message is erased with probability chi. So when is the outgoing message erased? Well, if at least one of the incoming messages is erased. The incoming messages must not be erased. Otherwise, we cannot recover the outgoing message. We need to have all of those guys in order to recover the outgoing message. So the outgoing message is erased if one out of those is erased. 2 out of those are erased, 3 out of those, and so on. So this is not so easy to calculate. Therefore, we look at the inverse argument. We ask ourselves, when is the outgoing message not erased? The outgoing message is not erased if and only if all the incoming messages are not erased. All the incoming messages are not erased, we can calculate the outgoing message, it's not erased. So probability that the outgoing message is not erased, 1 minus chi, and all the incoming messages must not be erased. That is equal to 1 minus xi. Again, we assume the incoming messages are all independent. So we can multiply the probabilities. So it's 1 minus xi to the power dc-1. And then we just rearrange this equation a tiny little bit, and we get chi is equal to 1 minus xi to the power dc-1. Okay, so now we can combine everything. So we look at what's going on. So we start with C1. C1 is epsilon times chi to the power dv-1. But we have no messages coming from the check nodes yet. Or the messages from the check node are erased with probability 0, dv-1. So this is equal to epsilon. So C1 is the probability of the messages that we send from the variable node towards the check nodes just after receiving them. They erased with probability epsilon. Then we execute the check nodes for the first time. So chi1 is equal to 1 minus C1 to the power dc-1. So this is equal to 1 minus epsilon to the power dc-1. Then we go to the variable node. So now we have the second execution of the variable nodes. We have xi2 is equal to epsilon times chi1 power dv minus 1. So this is epsilon times 1 minus epsilon power dc minus 1 to the power dv minus 1. And then we go again to the check notes. So we have chi2 is 1 minus c2 power dc minus 1. So this is 1 minus epsilon times 1 minus epsilon power dc minus 1 to the power dv minus 1, close the parentheses, to the power dc minus 1. You can see the expressions start to get very involved, and essentially we need to repeat this until we reach some CL, and CL is epsilon to the power chi L minus 1 to the power dv minus 1. And we can express this in terms of CL minus 1. So this is equal to epsilon times, now we insert chi L as a function of, or chi L minus 1 as a function of CL minus 1. So this is 1 minus CL minus 1 to the power dc minus 1 to the power dv minus 1. So essentially we have an iterative update equation. We can describe CL as a function of CL minus 1. This is an update equation, so we can iteratively evaluate and see how does CL evolve. So this is summarized in the slide again. So we start with C1 is equal to epsilon. Then we get chi1. That's just what we did before. Then we get C2. Then we get chi2, and so on. Eventually, we'll get an iterative update equation. CL plus 1 is equal to epsilon times 1 minus CL to the power dc minus 1 to the power dv minus 1. This is an update equation that you should know by heart, because this is a very fundamental equation that describes what's going on in LDPC codes. Because this is so fundamental, we also give it a name. So it's our update function f of epsilon CL. So it essentially describes the probability that at iteration L plus 1, the outgoing messages from the variable node are erased. This probability goes to 0. That means we have recovered all the variable nodes. So if for some L, CL becomes 0, we have recovered all the variable nodes. Okay. So it makes sense to check when this CL actually gets 0. And that's something we can do. That's something we will do as well. So we look at the decoder. We look at the probability that one bit finally is erased. So bit x hat is erased. And that's given by the total probability, where we sum up all dv incoming messages. So that probability is equal to epsilon times 1 minus CL power dc minus 1 power dv, because there we take all the dv incoming messages. So what we did before is we start the recursion with C0 is equal to 1. So it means all the incoming messages from the check nodes, they are erased. Then we can repeat the update. So we get C1 is equal to epsilon. And how long do we repeat this? So we repeat this until this evolvement doesn't evolve further. So when we have CL plus 1 equals CL, we are stuck. Then decoding just stops, and going further doesn't change, because we will always have CL at the input, we'll always have CL at the output, so we just get stuck and we say we are in a fixed point. The update doesn't yield further reduction in erasure probability. That's when we say we get stuck. Okay, so we have the update equation, and we can start by looking at a few properties of this update equation. The first property is what we check is the monotonicity. So will CL plus 1 get larger? So if we iterate, do we actually make the situation worse, or do we make the situation better? We don't want to make the situation worse. We want to stop when we make the situation worse. We want CL to decrease, because that means our erasure probability will drop. So therefore, the first thing we check is we check the monotonicity. And actually, we have a very reassuring result, because this update equation f of epsilon c is monotonically increasing in epsilon and in c. So it means if we increase epsilon, if we increase c, then the output will also increase. Decrease c, the output will also decrease. So the first one is very simple to see, because f of epsilon c is epsilon times some g of xi. So it's linear in epsilon. And hence, by definition of linearity, it's also monotonically increasing in epsilon. Then we assume that the check node degree is larger or equal than 2. And xi is a probability. It's between 0 and 1. So therefore, 1 minus xi is also between 0 and 1. And 1 minus xi to the power dc minus 1 is decreasing in xi. When we increase xi, this term will actually decrease. But then what we calculate 1 minus xi. Here there is a dc minus 1 missing. So that will actually be increasing in xi. So we have an expression 1 minus xi power dc minus 1 that is increasing in xi. So we have the monotonicity. Okay, so that is very nice. So it's monotonic with respect to epsilon and xi. Then we're looking at the monotonicity with respect to the iteration, which is the more interesting part, because what we say now is we start with some epsilon and some xi0, and we have our update equation. So now we have this sequence xl is a monotonic sequence. So xl is monotonically either increasing or decreasing. We see in xi it will be decreasing, and it will converge to the nearest solution of this fixed point equation. C is equal f of epsilon c. So it will converge somewhere. It will not converge anywhere. It will converge to the nearest fixed point. So let's prove this. We start with the first case, first simple case. C0 is equal to 0, or epsilon is equal to 0. That's easy, because then CL is equal to 0 for any L larger than 1. C0 is equal to 0 or epsilon is equal to 0, CL will always be equal to 0. Let's copy this expression so that we can actually see it on our slide, and so that you can always see what's going on. So we'll copy it up here. So if xi0 is equal to 0, this will be equal to 1, this will be equal to 0. And then CL plus 1 will be equal to 0. And that means the fixed point is equal to 0. C is equal to f of epsilon c is equal to 0. Okay, so this first case was not so interesting. The interesting case is the general case. So now we're looking at some L larger equal than 1. If we have the following situation, if we have CL is larger or equal than CL plus 1, CL minus 1, then we can calculate CL plus 1 is equal to F of epsilon CL. And because CL is larger or equal than CL minus 1, this is larger or equal than F of epsilon CL minus 1 because of monotonicity. And this is equal to CL. So if CL is larger or equal than CL minus 1, then CL plus 1 is larger or equal than CL. If we increase, if the sequence is increasing, it will keep on increasing. CL is larger or equal than CL minus 1, CL plus 1 will be larger or equal, CL plus 2 will be larger or equal, and so on. So it always climb. Okay, so we have this case. So now let's take a look at CL being smaller than, if CL is smaller or equal than CL minus 1, then CL plus 1 is equal to F of epsilon CL. And now because of monotonicity, this is smaller or equal than F of epsilon CL minus 1, which is equal to, by definition, CL. So also in that case, we have a decreasing. So if CL is smaller or equal than CL minus 1, CL plus 1 will be smaller, CL plus 2 will be smaller, and so on. So the first summary is that the sequence CL for L larger or equal than 0 is monotonic. Okay, so now we just need to prove that this monotonic sequence converges to the nearest fixed point. So we'll always decrease and get stuck, or we'll always increase and get stuck. So we're looking at some epsilon larger or equal than 0. That means that F of epsilon and C will be between 0 and epsilon, because this term is always smaller than 1. C is a probability, so this term will be between 0 and 1. This term will be between 0 and 1. So we have F of epsilon C always between 0 and epsilon. This is the case for all C in 0 and 1. So that means we can say that CL converges to some C infinity, which is between 0 and epsilon. C infinity is constrained between 0 and epsilon. So now, because F of epsilon C is continuous, it means that C infinity is equal to F of epsilon C infinity. That's a fixed point. So now we need to show that this fixed point is the nearest. Nearest meaning in sense of monotonicity. So it remains to show that C infinity is the nearest fixed point in the sense of monotonicity. So, how do we prove this? Well, we start by considering the fixed point theta. So this is a teaching in Greek letters. We know the Greek letters from COVID, and here we learn some different Greek letters. So we have a fixed point theta such that CL of C0 is smaller or equal than theta for some L larger or equal than 0. So we have one, we know theta is a fixed point, CL is smaller or equal than this fixed point. So now we calculate CL plus 1, and we start in C0. So this is C0. So this is equal of F of epsilon CL when you start in C0. And this is because CL is smaller or equal than theta. This is smaller or equal than F of epsilon theta, which is equal, because it's a fixed point, is equal to theta. So we can reason that C infinity is smaller or equal than theta. We have a fixed point, and if CL is smaller or equal than this fixed point, we will converge to something that will stay smaller or equal than this fixed point. Cannot go beyond this fixed point. It will stay forever smaller or equal than this fixed point. So now we need to prove the other direction if we're coming from the other side. So very similarly, we have CL of C0 is larger or equal than theta for some L larger or equal than 0. Then we have CL plus 1 of C0, we do the same exact reasoning, is equal to F of epsilon CL of C0. And this is larger or equal because of the monotonicity again. CL is larger or equal than theta. F of epsilon CL is larger or equal than F of epsilon theta. And theta is a fixed point, so this is equal to theta. Because we have a fixed point, that means that F of epsilon theta is equal to theta. That's what we are using in this equation. So what does that mean? That means again that C infinity is larger or equal than theta. So again, we cannot jump over this fixed point. We'll move towards a fixed point, but we'll stay above. So if either we are above, then we move towards it, or we are below, and then we move towards it. So the conclusion is that CL cannot jump over a fixed point, and it will converge to the nearest one. Okay, so we have proven the convergence here. Okay, so we have now two properties. We have this property of continuousness, and we have the property that will converge to the nearest fixed point. Then we have a third property, which is the monotonicity with respect to the channel, which says that for some epsilon between 0 and 1, this sequence CL converges. If the sequence converges for some epsilon, will also converge for all epsilon that are small or equal, or for all epsilon prime small or equal. What does that mean in practice? This means if we can decode for some epsilon, we can decode for any epsilon that is smaller. We can decode for the better channels. We can decode for a bad channel. Every channel that is better can also be decoded. Kind of clear, but not necessarily obvious. It may happen that for some bad channel we can decode, but for the different channel we can decode. Yeah, we proved that in this case it's not the same. So how do we prove this? Well, this is pretty easy. Again, we use the monotonicity. So epsilon prime is small or equal than epsilon. And we assume that CL of epsilon prime is smaller or equal than CL of epsilon. So then we calculate CL plus 1 of epsilon prime. This is equal to f of epsilon CL for epsilon prime. This is smaller or equal than f of epsilon CL plus 1, which is CL plus 1 of epsilon. So we have, if CL of epsilon prime is smaller or equal than CL of epsilon, then CL plus 1 of epsilon prime is smaller or equal than CL plus 1 when we start with epsilon. And because epsilon prime is smaller or equal than epsilon, we start with C1 of epsilon prime, which is smaller than C1 of epsilon. We show that C1 of epsilon when we start with epsilon prime is smaller or equal than C1 when we start with epsilon. And we have shown that CL plus 1, so if CL of epsilon prime is smaller or equal than CL when we start with epsilon, then the same is also true for CL plus 1 when we start with epsilon. So we have all the ingredients for a nice little proof by induction. So we can use this proof by induction, and we get that any CL of epsilon prime is smaller or equal than CL of epsilon. Which means if this sequence CL of epsilon converges to 0, because this one is always smaller or equal, then by the sandwich theorem, this sequence will also converge to 0. And we have shown monotonicity holds as well. So let's take a look at an example. So we start with one configuration of a code, which is the regular 2-4 code. Grab node degree 2, check node degree 4. The rate of the code design rate is 1 minus dv over dc, and this is 1 minus 2 over 4, so it's 1/2. And we vary epsilon, so we start with an epsilon of 0.45. We see we start at 0.45, so we start at epsilon, and we converge. At some point, we get stuck. Here we show CL as a function of the iteration. So this is actually C infinity, which is equal to 0.289 something. So we get stuck. The coding doesn't work. We cannot recover on average the variable nodes. So let's decrease epsilon a little. Decrease epsilon to 0.4. So again, we start at 0.4 and we plot the behavior of CL over the iterations, and again, we get stuck. No movement anymore. So let's decrease epsilon a little bit further. 0.35 still doesn't work. Okay, so we get stuck again and cannot converge. So let's look further. 0.34. Not really, maybe it happens, but still we are barely above 0 and will not come. Make it a tiny, it looks very good. We are almost there here. So make it a tiny bit smaller, 0.33. And now we see that after some few hundred iterations, we'll actually converge to 0. So again, this is not the behavior of a specific code. This is the average behavior of an idealized code. So we don't have any specific connections of variable nodes and check nodes. We have a very idealized scenario. And essentially, this is also, we assume that the code is infinitely large. We assume the messages are independent, which means we need to have some structure that has no cycles. Well, wait a little bit. We saw that we cannot construct codes without cycles that have variable node degree, minimum distance larger than 2. So they don't exist. That's true. What we do here is we construct a code that has cycles that are so long that they will not matter until iteration 200. So the smallest cycle is 1000 long. Essentially, this is called, we construct a tree, but we don't close the code yet. But we assume that the code is so long that the cycles only play an effect after we do the few hundred iterations. So that's why we can make this argument. Okay, so this is not so promising. Epsilon of 33%. The code rate is 1/2, so the capacity is also 1/2. So in an ideal capacity achieving code with an epsilon of 0.5, we are able to decode. With this LDPC code, we can construct a very long code, infinitely long. We will not be able to decode unless epsilon is smaller or equal than 0.33. So we need to think of something else. So let's take a further look. So again, we see that if we further decrease epsilon, the convergence gets faster. So here we are there already after 50 iterations. And for epsilon equals 0.2, already after 10 iterations. So let's take a look at a different code. So we have 3.6 LDPC code. So it has variable node degree 3 and check node degree 6. The rate is 1 minus dv over dc, so it's also 1/2. Again, let's start with epsilon of 0.45. And we see we start at 0.45 and we get stuck. Decoding doesn't work. Okay. So we are not capacity achieving. We still have a gap to the capacity. So we need to have a different look at a different code. Or so we decrease epsilon a little bit, 0.44, no chance. We are in a fixed point, we get stuck. Further decrease, epsilon equals 0.43, no chance. So let's decrease a little bit further, 0.4292. And what we see here is we have a steady decrease, and eventually we will reach 0. 200 iterations, we have reached 0. So this code converges. For epsilon equals 0.43, we get stuck. We're in a fixed point. For epsilon equals 0.4292, it takes some time, but we have a steady decrease, and eventually we will converge. Very nice. This is significantly better than what we had before, and we have a pretty good code with a pretty solid performance. So let's take a look at what happens if we decrease further. If we have 0.42, so we decrease just a little bit further. We converge already after 30 iterations, 190 something iterations. And if we decrease further, 0.41, after 20 iterations, we're done. So this summarizes it. So you see that there is some phase change, and some epsilon will decrease very rapidly, and we can decode our code. Very nice. So some words of caution. The analysis that I showed here holds only for asymptotically large codes, so n must go to infinity. Because of the reasons I just said, we don't need to have cycles, but we cannot construct a good code without cycles. So we need to make the code as long as possible so that the cycles are as large as we can have and they don't play a role for the analysis. So if you have a code with finite n, the performance may deviate from the results of the analysis. But the analysis shows us what we can expect at most from a code. The best possible code that we can design will have this performance. So epsilon equals 0.4292. It will rapidly drop in performance and on error rate and will be able to decode. So the analysis of the performance for a finite length n is not trivial, and there are still research papers coming up that tackle this problem. And in the next chapter, we'll take a close look of what happens for finite n. So let's look at an example. So here's the example of this code. 3.6 code, and we run some simulations. And we saw that for 0.4292, which is 4292, somewhere around here, the performance should actually look like this. So we have an error rate that goes to 0, and we are above, then we'll have a finite error rate. So this is actually what the ideal decoding would look like when n goes to infinity. This is 0.4292. And what we see here is the following. We see that if we actually construct codes, then the performance is pretty far away from those. But if we increase n, so these are just some codes that have been constructed, and if we increase n, we approach the performance of the ideal code. This is the threshold that we mentioned in the previous chapter. So that there is a threshold at which the error rate drops rapidly. We have just calculated or determined numerically a threshold. And the code performance, if we increase n, will actually move towards this threshold. So that's the example. Now, how can we define this threshold formally? The threshold is defined as follows. So first, the threshold is denoted by epsilon star, and the threshold depends on the parameters of the code, dv and dc. And it's defined as the largest epsilon. Epsilon star is the largest epsilon. Supremum means it's just the largest. The largest epsilon is a probability, so it must be between 0 and 1, such that CL is equal to f of epsilon CL minus 1, so that we have a fixed point. So that we have this update equation converge to 0. So this update equation CL should converge to 0 if we start with C0 equal to 1 and if L goes to infinity. So it's the largest epsilon for which this update equation converges to 0. Previous example, it was 4292. We can also characterize it using the fixed point. That's a little bit helping us to calculate it. So how can we do this? We can do this as follows. So we have epsilon star. That's the largest epsilon for which this fixed point equation has no solution for xi in 0 and 1. So we exclude 0 here. This is important. We exclude 0. So what does this mean? It means we have no fixed point except when xi is equal to 0. Xi equal to 0 is the trivial fixed point. This one is always there. If it has converged, we are at xi equals 0, and we have a fixed point because we cannot converge any further. This is where we get stuck. So we have this fixed point equation, and this fixed point equation has no solution if we are between 0 and 1, excluding 0. And it's the largest epsilon for which this one has no solution. That's one way of looking at it. Another way of looking at it is that we're looking at where does a fixed point happen? If there is a fixed point, so if xi equal to f of epsilon xi has a solution for some xi different from 0, that means we cannot decode. So we look at the smallest epsilon where we cannot decode. This is the threshold because that's where the change happens. Our smallest epsilon for which we cannot decode, and if we decrease epsilon by a tiny little bit, small epsilon, this epsilon by a small epsilon, so we decrease epsilon a tiny little bit, then we can decode. So that's the fixed point characterization, and that's the one that we use in the following to obtain the thresholds. So let's do the following. We have a fixed point equation. So if xi is equal to f of epsilon xi, and xi is larger than 0, means decoding gets stuck. There is no chance that xi will further decrease, eventually reach 0. So how can we determine the threshold? So here is a visual aid for determining the threshold. So threshold or fixed point means f of epsilon xi is equal to xi. So what we do is we plot xi and we plot f of epsilon xi. We see that there is a fixed point at 0, but we are not interested in that one. So if f of epsilon xi equals xi, means that this function f of epsilon xi crosses the 45-degree diagonal. For instance, here we have a fixed point. F of epsilon xi is equal to xi. This is just, this dashed line is just xi. So here we have a fixed point and decoding gets stuck. Here we have a fixed point and decoding gets stuck. For epsilon equals 0.334, we need to look very closely here, but there we'll also have a fixed point, decoding will get stuck. And for epsilon 0.2, we see very clearly there is no fixed point. Even if we zoom in to the bottom here very closely, there will be no fixed point. So decoding will not get stuck. Okay, so let's take a look at the other code. So this is the 3.6 code. So we see that for epsilon equals 0.5, we have fixed points. We actually have one fixed point, second fixed point. We actually have two fixed points. So decoding will get stuck in this fixed point. There's no way that we can reach this fixed point, because we cannot jump over the fixed point. When we start from here, we'll get stuck in this fixed point. So we start with 0.45 and we'll get stuck in this fixed point. There's no way that we can reach this one, but we'll reach this one. Sorry. So now for epsilon equals 0.4292, it's this curve, we see that we don't touch the xi curve, the dashed line. We stay very closely below this dashed line. And then if we decrease epsilon further, we decrease the dashed lines further, and we see that there is no crossing, means no fixed point. But we see already this visualization is nice, but not too nice, because we need to mess in this 45-degree diagonal. So that's a little bit difficult. But what we can do is we can rewrite the fixed point equation a little bit to simplify expression. So what we can do is the following. So if c is equal to f of epsilon c characterizes the threshold, then we can just rewrite this a little bit and say we have a threshold or we have a fixed point if f of epsilon c minus c is equal to 0. That's a different characterization of the fixed point. So what we can do is we plot f of epsilon c minus c for all the values of c between 0 and 1, and we check if this equation is equal to 0. So if f of epsilon c minus c is smaller than 0 for all c between 0 and 1, excluding 0, then we converge. And the largest epsilon for which f of epsilon c minus c is smaller than 0 is the threshold. We have a Jupyter notebook for showcasing this, and we can quickly go there and see how this looks like. So this is our Jupyter notebook, and we can start. Here we have some code for calculating the fixed point and for plotting the fixed point, and this is what we get. So we can take a look at the parameters of the code, and what we see here in the plot is the following. So we can change epsilon. Let's see if I can increase the size a little bit. There we go. So here we can change epsilon, and we see if there is convergence. So if we start with epsilon equals 0.45, then we can see there is a fixed point here. The curve crosses 0, and we cannot decode. But if we decrease to 0.4292, gets green, it means we don't cross 0, and we have a curve that no fixed point, and we can actually decode. So let's see what happens if we change the parameters of the code. 2.4 we saw already we cannot decode. So what happens if we increase dvntc? So that with 3.6, rate 1 half code, we can decode. What happens if we go to 4.8? We cannot decode. So we have fixed points again. So let's see what happens if we go to 5 and 10. We cannot decode. So 3.6 seems to be a pretty good choice. So let's go to 6 and 12. Cannot decode. 7 and 14. We cannot decode. Okay, so let's take a look at 4 and 8. That was the next one. So we decrease epsilon a little bit and see if we can decode. We need to go to 0.38, and then we can decode. So there's a significant gap between where we can decode with 6 and with 4.8. So that's something you can play around with a little bit. And you also have the update equation that you can see here. So here we have the update. It's calculating a little bit. Up. Moment. So let me wiggle a little bit. 3.6, we have 0.432. And there should be a picture. Now this is the unwanted effect. So where's my picture? There we go. Okay. So here we have the f of epsilon c as a function of the iteration. So for 3.6, we saw that for 0.4292, we can decode. So for 0.43, we get stuck. And how does the situation for 4 and 8 look like? Well, we need to go to 0.38 something, 389, 380, we can decode, 382, we can decode, 384, we cannot decode. So 383 is where we can start. Okay, this stops after 100 iterations, but you see that this will likely decrease. We can spend more than 100 iterations. So this is for your convenience. You can play around with these a little bit and get used to this update equation. So here we also see this in a slide, what I just showed in the Jupyter notebook. So here we have this fixed point characterization for the 2.4 code, and the same for the 3.6 code. So here we see that we have the two fixed points. If we get stuck, we have these two fixed points, but for 0.4292, we'll be conveniently underneath 0, and that means that we actually are able to decode. All right, so now we can also calculate this threshold numerically. So how can we do this? Let's take a look at the update equations a little bit. So we know that this threshold epsilon star is the smallest epsilon for which the fixed point equation has a solution, or the largest epsilon such that CL converges to 0. So we start with this fixed point equation. CL is equal to epsilon of 1 minus xc power dc minus 1 power dv minus 1. And we solve this for epsilon. So we say that epsilon is equal to xc divided by 1 minus xc power dc minus 1 power dv minus 1. And we define the right-hand side to be equal to g of xc. This equation has a nice property, because if c is smaller or equal than g of xc, that means that c is larger or equal than c times 1 minus xc power dc minus 1 power dv minus 1. So it means that if epsilon is equal to xc, then we get stuck, we cannot decode. That means we have an upper bound of the threshold. So if this is the case, if xc is smaller or equal than g of xc, then xc will be a bound of the threshold, because it's an epsilon where we cannot decode, so it must be larger than the threshold. So we would like to find the smallest g of xc, which is the smallest epsilon that we can decode. So let's start with a simple case. We start with dv equals 2, because then dv minus 1 falls away, and g of xc is equal to xc divided by 1 minus xc to the power dv minus 1. So instead of minimizing g of xc in this interval, we can also look at g of 1 minus xc. So we make a change of variable. C, we're looking at some xc prime, which is 1 minus xc. And then we use the truncated geometric series. We use s equals to the sum from 0 to eta minus 1 of tau to the power I. And I can never remember this, but there is a very simple trick to prove this quickly. So what you can do is you can calculate s minus tau times s, which is equal to 1 minus tau times s. And this is equal to the sum from I equals 0 to eta minus 1 of tau to the power I, minus, now we multiply everything by tau, which is the sum from I equals 1, eta minus eta of tau to the power I. So this is equal to 1 plus tau square plus tau to the power eta minus 1 minus tau squared minus tau to the power eta. So this is a so-called telescoping series, and we can cancel all these terms except the two at the boundaries. So this is equal to 1 minus tau to the power eta. So therefore we can say that s is equal to 1 minus tau to the power eta divided by 1 minus tau. This is the truncated geometric series. And this is what we're going to use. So we express g of 1 minus xc is equal to 1 minus xc divided by 1 minus xc power dc minus 1. This is exactly what we have here, just flipped. This is equal to 1 divided by this sum here. 1 plus xc square up to xc to the power eta minus 1, so it's dc minus 2. So when is this minimized? This is minimized if this sum is maximized because it's in the denominator. So when is this maximized? This is maximized if xc is equal to 1. C is equal to 1, the sum is equal to dc minus 1. Because there are a total number of dc minus 1 terms. Each of those terms is 1, so it's dc minus 1. Okay, so what do we have? We have a threshold now for the regular 2-4 codes. So because g of c is the threshold, minimize it, and that's 1 over dc minus 1. So the threshold for a code with variable node degree 2 and check node degree dc is 1 over dc minus 1. And we saw, for instance, dv equals 2 and dc equals 4, means epsilon star is 1/3, which is 0.333. This is exactly what we saw in our numerical evaluation previously. We will see later that such codes are not very good codes. They will have some bad properties in terms of minimum distance. First, let's take a look at the general case. If dv is larger or equal than 3, situation is getting out of hand. So situation is not easy. Situation is not easy when dv is larger or equal. Because then we need to minimize this g of xc, which is looking rather unpleasant. G of 1 minus xc is looking similarly unpleasant. But what we can do is we can try to minimize it. How do we do this? Take the first derivative. So take the first derivative of g of xc and set the result to 0. Don't do this. What you can do is you can do this, try this for yourself. So you square the denominator and then you calculate the difference of this minus the gradient of the derivative of the denominator minus the gradient of this, derivative of this, plus times the denominator. Then if you multiply this and factor out everything, what you get and set the result to 0 is this expression. So this is a good exercise. Try to take the derivative of this, set to 0, and see if you come up with the same solution or with the same expression. If not, we can discuss this in the discussion session. So we have this, it's a polynomial actually in xc with terms c power dc minus 1, c power dc, and that's it. So we can see it has a trivial root for c is equal to 1, but this would be a very bad upper bound for the gradient because we have this expression. So if c is smaller or equal than g of xc, then it's an upper bound to the threshold, which is 1 in this case. So it's not a very good bound. So we need to reformulate this. So we massage the expression a little bit, and we get the following expression. So what we get is the following one. So we get this times c minus 1 plus 1 minus c power dc minus 2, which is equal to 0. And now we divide both sides by 1 minus xc. Then we get the following. So 1 minus xc is between it's not equal to 0 because we don't want xc to be equal to 1. That's a trivial solution. So what we get is this term minus 1 minus xc to power dc minus 2 divided by 1 minus xc. Again, we use the same trick. We use the truncated geometric series. So we have this term minus the sum of xc to the power I. So it's another polynomial. It's a polynomial with largest degree dc minus 2. And then we subtract just xc to the power dc minus 3, xc power dc minus 4, until we get to c to the power 0. Now we use Descartes' rule of sign. Descartes' rule of sign is a very nice way of telling us how many roots that are real polynomial has. So if we have a polynomial f of x, and if the coefficients m are ordered, and if all, or the exponents, they are ordered, so m1, small equal than m2, small equal than m3, and so on, and all the coefficients are unequal to 0, then we can say the number of positive real roots of this polynomial is upper bounded by the number of sign changes between consecutive coefficients. So we look at the coefficients, the first coefficient, second coefficient, third coefficient, and we look at how often does the sign change. When the sign changes, that means we have all the sign changes, we accumulate them, and this gives us an upper bound on the number of roots. So here we can see this is a positive sign, and these are negative signs. One sign change, we have at most one positive real root. So you can say the equation has at most a single positive real root. So g of xc has at least one minimum between 0 and 1. So therefore, it has exactly one positive real root. How can we compute these roots? This is not easy. There are some closed form solutions of calculating the roots of higher order polynomials, but they are also not trivial. We can use computer algebra software like Mathematica to express the roots. Usually, it's simpler to do this numerically. So here are some examples. First example is for dv equals 3 and dc equals 4. That's something that you can do with pen and paper. So the polynomial looks like this, so it's essentially quadratic, and it has a positive solution xc star, which is 1 plus square root of 21 over 10. And then we must bring this 1 minus xc star into the fixed point equation, and we get this rather unpleasantly looking expression, which is 0.647. That's the easy one. Now let's take a look at some other examples, the 3-6 code. And for 3-6, we can actually get the solution, but it's far from being trivial. So we need to calculate first sigma, given by this rather unpleasant expression, where we have a and b. A is given by this guy, and b is given by this guy. So again, rather unpleasant. And then we can calculate the threshold by taking 1 minus sigma over 1 minus sigma power 5 squared. So in principle, we have an analytical closed form solution. But before you type in this into a program to get the result, it's actually easier to write the program to do it numerically. And you'll find that this is equal to 0.42944. So this is what we saw. We saw for 0.4292, we converge. For 0.4295, we don't converge, and that's because the threshold is 0.4244. Here are some more examples. We have the 4-6 code. I won't go into detail, but you see the expressions are similarly unpleasant. And for 3-5 code, you have a similar expression. So here is the thresholds of some regular codes of rate 1/2. Sine rate 1/2. So dv is equal to v and dc is equal to 2 times dv. For dv equals 2, we saw that the threshold is equal to 1/3, or 0.33. Here we have 0.4292 for 4. And then if we increase dv, is already what we saw in the example, the threshold will actually decrease. So the best code on the binary erasure channel has a threshold that is obtained at 0.4292. The best parameter are 3 and 6. So verbal knot degree of 3 and check knot degree of 6. But we still see that there is a significant gap to the capacity here. This gap is one that we will close soon, but it still exists. So this is an example for rate 3/4. So here we have, here we have dc equals to 4 times dv, and here we have an epsilon star for dv equals 2, which is 1/, we call this 1/, dc minus 1. So dc is 4 times dv, so it's 8, it's 1/7 in this case. Rather bad. And then again, we have the best threshold for dv equals 3. And then the threshold further decrease. Again, we see that there is some significant gap here that we will to close. All right, so we have analyzed the performance of some code, and we find that verbal knot degree 3 seems to be the best or very good solution, and that's the result of this very first chapter. So we have done an analysis of LDPC codes, and now we'll look a little bit further into some properties of those regular LDPC codes.